Hello friends, in this session we will see relative stability using Bode plot. We will also see the gain margin, phase margin, omega GC, omega PC. Let us begin. So if you remember, I had told you that in order to find the relative stability using a Bode plot, what you need actually, you cannot do it on a approximate plot, because for this you need exact Bode plot. What do you mean by exact plot? Exact plot in the sense, definitely magnitude, all values from omega equal to 0 to infinity has to be known. Similarly for phase, if you see, all values from omega equal to 0 to infinity has to be known, right? So exact Bode plot has to be known, then only you can find the relative stability using Bode plot. But it is impossible, right? So just for understanding purpose, let us see that even if you have asymptotic plot, let us try to find something out of it. Okay, let me take one system. Consider a system. Okay, yes. So the upper half, if you see, it is representing the gain or the magnitude, and the lower half, if you see, it is going to represent you the phase, right? Now and then we have got these two corner frequencies, omega 1, omega 2, right? Omega 1, omega 2, the same frequencies are there. Is that fine? Yes. Now let us think of something great. Let us see what is happening at this point. If you see that this particular one, this is 0 dB line, right? If you see my gain plot or my magnitude, it is crossing 0 dB at this point, and it means it is what? It is nothing but gain crossover frequency, because if you remember, gain crossover frequency is a frequency at which my magnitude plot is equal to 1, or we can say 0 dB, because if it is 1, then 20 log of 1 is what? It is going to be 0 dB, right? In dB, if you think of magnitude, it is going to be 0 dB, which means this particular frequency is nothing but what? Omega GC. So, and we also know that we have seen that if omega GC is this, then at omega GC point you get what? You get phase margin. So this is omega GC, then here you definitely get, you have to project this here, so this is nothing but omega PM. At omega GC you get PM, which is nothing but the phase margin. Getting my point? Yes. Now another thing, if you observe what has happened here, this orange, if you observe what has happened here, my phase plot crossed minus 180 degrees, which means this frequency is definitely what? This is going to be definitely omega PC. So at this omega PC, if I project this up this way, right, up to this plot, magnitude plot, then here to here, what do I get is, then from here to 0 dB, with respect to 0 dB, you get this one as GM, gain margin. Getting my point? Which means what? This is nothing but the gain margin, and this is nothing but the phase margin. Now what I'm saying, how to identify whether it is negative or positive? That is the question, right? So if you think of, if this is minus 180, then it's definitely, let us say this one is, let us say minus 270, right? Let me call this as minus 270 degrees. This has minus 270 degrees. If you remember what happened there, you remember this polar plot this way, right? If it goes like this, and this is minus 1 point, right? This is minus 180 degrees. If it goes like this is the plot, then what is going to happen? It is definitely going to encircle it. It is definitely going to encircle it. Getting my point, right? Which means it can be unstable, and it is unstable when PM is negative. Now this angle is what? This angle is what? This angle is definitely from minus 180 degrees, and this is minus 270 degrees, right? So if you think of this angle is what? It is definitely more than minus 180 degrees, or you can say with the sign, if you think of, it is definitely less than minus 180 degrees, because minus 270 degrees is going to be less than minus 180 degrees, right? Which means if you think of this PM here, this PM here, this phase margin is going to be what? Because if this is minus 270 degrees, or let us say, because it is less than minus 180 degrees, since it is less than minus 180 degrees, it means that system can become unstable. It means it is negative, because we have seen that whenever phase margin or the gain margin is negative, system is going to be unstable. So this indicates that it is a negative phase margin. Am I right? Yes. Now if you think of gain margin, what is happening here? Let us see. Do you agree with me that this is 0 dB? If you remember, I had told you that this is minus 1, right? I had told you that your plot can go like this, your plot can even go like this, but it should not go beyond this magnitude 1, beyond this magnitude 1. Now if you see in your magnitude plot, in your magnitude plot, right, if you just think of in your magnitude plot, now just imagine, let me consider, let us take 20 log of 0.5. What does that come? Let us try to find out. This becomes minus 6.02 dB. Now let me find 20 log of 1.5. Let us see what happens. It becomes positive 3.5 dB. Now you check out. See, do you agree that if this is 1, if you remember the plot this way, if this is 1, okay, minus 180 degrees, minus 1 only, but just considering the magnitude, okay, and if this is 0.5, this is 0.5, what does that mean? What does that mean? There is sufficient margin over here, right? There is sufficient gain margin over here. But what happens? What happens if this plot, rather than 0.5, if it goes like this at 1.5, then what is happening? What is happening? You have this extra gain. You have this extra gain, right? You have got this extra gain, and this is not the gain margin. Rather, this is negative gain margin. Rather, you can say that GM is negative over here. Why? Why? Because this is extra. Because this is not a margin. This is a gain which has to be removed from the system. Why? Because of this, system has already become unstable. System has become already unstable. It means that, now see what happened when I put 20 log of 1.5. When I put 20 log of 1.5, I got some positive value. Got some positive value. Whereas when I put 0.5, I got I got a negative value. I got a negative value, which means if my magnitude is positive, because here if you see, definitely this can either be 25 dB or anything, it can be there. Let us consider this much, 25 dB. What is that? Is it positive? It is positive, which means gain margin has to be negative, because we have seen that the moment 20 log of 1.5 is positive, and we know that it is going to, that the gain margin is going to be negative, then yes, definitely whenever my dB value is positive, whenever dB value is whenever dB value is positive, gain margin is negative. Getting my point, right? Yes. So that's also, what do you understand from this? You have seen that gain margin is also negative and phase margin is also negative, which means system is unstable, right? Now I want to make a very important observation. What is that observation? Let us see. I am saying that an important observation over here. What do you understand? You have seen that this is omega PC, right? Yes. And this is omega GC, right? Yes. So if you check out, omega gc is greater than omega pc or not, and when omega gc is greater than omega pc, what has happened? System has become unstable or not? What does this mean? What does this mean? This means that for stable system, what should happen? What should happen? If for unstable system omega dc is greater than omega pc, then for stable system omega pc should be greater than omega gc, or we say omega gc should be less than omega pc. And in case of unstable systems, or in case of unstable system, what is there? Omega pc is less than omega gc. So you can basically keep these 2 points in your brain, that whenever omega pc is greater than omega gc, system is stable. Whenever omega pc is less than omega gc, system is unstable. That's it. This is a very important observation which we have found out. Anyways, now our complete frequency domain analysis has been accomplished. We have completed everything related to the frequency domain analysis. Now after this, we will start a very important topic called as compensators. Okay, thank you.